There it goes. So the other file that we were recording, I think it probably got cut off a little bit, but it should mostly be there. The way the file that it uses should be okay still. I'll make sure of that. And yeah, I think, what was I trying to do? Okay, we're going to open up this slide one more time. Where was I? Here. So, okay. Do I have things I can click again? I'll probably have to restart my computer after all this. I tried weird things. Okay, so we're trying to prioritize B's over A's, and that means they were closer to 42 than the A's were. Yes? And so what you'll do is you'll be like, all right, is the distance from B to 42 closer than the distance from A to 42? Does that make sense? So you'd be like, all right, the distance from B to 42 is the absolute value of B minus 42, yeah? The distance from A to 42 is the absolute value of A minus 42, or 42 minus A, whichever way you want to think about it. And you just you want to prioritize B's when that distance is smaller than the distance for A's. So that's what you'd return. Something like that. Does that make sense? So that would give you a priority queue that would prioritize numbers that are closer to 42. And that is a valid way to prioritize things. All right, that's a type of ordering that you could do. Are there any questions about that? It's very weird, very cool, I think. All right, if we're happy, I think it's time to give you a lab, because I have some things I want to tell you about using GDB for that lab. You ready for that? All right, maybe while you're doing the lab, I can install a virtual machine and show the cool stuff. But let's release that lab for now. This is lab 8. Be due in a few weeks, plenty of time after the midterm, right? Okay. But let's go look at it together. This one is about binary search trees, and we're going to use Pokemon as a theme. You have 3 weeks to do this lab. There is a reason it is a 3-week lab. Okay? Read the meme. And it will all work out. So let's go to the code. Okay. Start code 41, lab 8. What do we have? We have all of these things. We will be making binary search trees in which you can store Pokemon. All right. So your goal is to implement binary search tree bst.cpp from bst.h. All right, it's just a binary search tree class with not boring integers as the node values, as the node keys, but it will be Pokemon values. So here's what it means to be a Pokemon in terms of our code. It's going to be every Pokemon has a number associated with, like Pikachu is number 25. You got a name of your Pokemon. You got a type, like electric type or something. And yeah, I've made there's going to be a toString function on Pokemon. I think I maybe gave that to you. And then here's your binary search tree BST type, okay? Your BST class wraps around the idea of a binary search tree where you can do stuff, all right? So it's got a constructor that makes an empty tree. It's got an insert method called catch. You catch a Pokemon to add it to your tree. Release is the opposite of catch, so that's going to be deletion from your tree. There's going to be a search process that gives back a pointer to a Pokemon. So this is going to be a BST that has key value pairs. So it's essentially you making the map type in C++. Okay, so the keys of your binary search tree are going to be the numbers of the Pokemon, like 25 for Pikachu, and then the values of the BST, the things stored associated with each key, which we'll call data, is going to be the Pokemon themselves, the whole object, the whole struct with the name, the number, the type. Okay, so yeah, you want to be able to search for Pokemon by their key, and the values associated with each Pokemon at all the nodes is just an object of the Pokemon struct type. And you'll give back a pointer to that so that you can give back null if it's not there. So that's an easy way without like throwing an exception or something to do that. So that'll work. What else? And then we've got a traversal. So I want, there's a way, like I'm just going to go through your tree. I've given an in-order traversal of the Pokemon that are in it, and turn them into strings so that I can test you with that. And then, for debugging purposes, I've made this lovely method for you that I'll explain later. all right? But here's what the tree looks like. This is your one member variable, all right? All you need to have a binary search tree is to know who the root is, right? The root is a BST node star, okay? And so what is a BST node? It's the type just for us, the implementers of the class. It's a private thing just for us. You can just use it as normal though. We've been doing something like this before, right? So a BST node holds key value pairs and everything else that you need for a node, right? So the key type is this, the data type, the value associated with the key is that, the Pokemon object. And then you can go left, you can go right, and you can get your parent. So those are the 3 pointers to other nodes in the tree. Does that make sense? So instead of like string keys, int values for like a phone book, we have int keys and Pokemon values. Everything else is as a tree would, as you would expect in a tree. Okay. So yeah, there are in-order traversals, a helper function for searching that gives you back the node the pointer to the node itself that you can use when you're giving the user, you're implementing this function for the user or this method for the user. Because you don't want to give them back nodes. You want to give them back things they want. Pokemon values, right? Nodes are just for us. So this is just helper methods for us, okay? We can think of them as functions. Here's a remove method, helper function, that takes a BST node with that you want to get rid of, and it does the process. So like you can use these in these like user-facing functions. These are supposed to be pretty things that we give to the user, but you need to get down to the nitty-gritty stuff with pointers, and so these are just for you. They will help you. Like you can call these from the user ones, okay? And then I'm going to force you to use predecessor when you're doing the two-children removal case, okay? So I'll have you implement this. So given a node of the tree, go and find the predecessor for it. Give back the pointer to that node. Okay, so that's what it means to be a predecessor. You give me one node, find the predecessor of it, give back a pointer to it. All right, so you can copy and paste a lot of my successor code from class for that. And that's mostly it. You're going to go to bst.cpp and implement all these things. So I've given you a lot of stuff. So toString is done. You have to do the constructor. How do you make the tree start out empty? You've got a root pointer, set it to something, right? So that's the constructor. Insert is catch. So like you have a new Pokemon, you've caught it. So you want to insert that into the tree. So you're going to make a new node on the heap and then do the insertion. The key is going to be the number of the Pokemon, which lives inside the Pokemon object, and the data is the whole type P, the whole Pokemon P itself. And then yeah, just remember all the cases. If the tree is initially empty, the first Pokemon you catch becomes the root when you turn it into a node, right? So remember that. Otherwise, you have to search, right? Search for where it should go and add it to that spot. If you already see it, then if it's already in there, just like do nothing, because there's no other way. There's no like replace the value. The Pokemon's value is always the same. So there's that, and then yeah, just like add a new one if it's not already there. So you can use your search process to do that and make it quicker for you. So like remember to rely on yourself, the other things that you've made for yourself throughout this lab. All right, it's like you could totally call search in this method to help yourself, like see if it's already there. Okay, so here's your helper function search. So search for a key, traverse the tree, go and see if you find it, return null if it's not there, return the BST node pointer if it is there. There's all that. Yeah, so that's the search, which is very similar to things we've done. And then this is the user-facing search. I hope that you could see how, like, I've already done this for you, but I hope you can see like the whole point of like this is what we implement as we get it down to the nitty-gritty. We do pointer stuff, and then when the user wants to search for a Pokemon, they're giving us the key. We're going to call our own search and get back a BST node star, like where in the actual tree was it? Give me the node. If there was nothing there, we will have given back null. If so, we'll just say user, there is no Pokemon object. I give back null to you. Otherwise, we give back the Pokemon that was inside of that node that we got. Okay, because that's what the user really wanted. Give back a pointer to it though, and arrow data the address of that. Okay, so this one's already done for you. You don't have to worry about it. But do you see how it's using the search that you will make to make a pretty version for just the user? Okay, or they don't have to deal with nodes and things. They can just deal with the Pokemon values that they get back. Okay, so there's that. I've also done the in-order stuff. There's a traversal, like I'm going to calculate a string of all of the nodes in your tree so that I can test you based on that. It's like there should be a certain order for the in-order traversal, right? It should be sorted. That's how that should work. And then, yeah, you got predecessor. So go find the predecessor of a node. Just return null if there is no predecessor. But in theory, you're only ever calling predecessor from the two children case, so you can be lazy if you want to, technically. So yeah, just do that. Predecessor, given a node, go find the predecessor, give a pointer to it. And then you'll be using that in remove. So let me do these backwards. So remove, you've got a node pointer. Do your removal. All right. So, you got your leaf case, your one child case, your two children case. That's the case where you call on your predecessor and you do the swapping and then you delete the predecessor node at that point because it's an easier one. It's one of these two cases, so it's like recursive. Also, remember that your book has pseudocode for all of this. Like, you are not alone. Remember that you can go looking at that. That's okay. So that's removal from a tree node. The user is going to call it release. So they're going to ask for a key. Go and get rid of that key and its value from the tree. So I think you can hopefully see, like, call search, get a node pointer. If it's not there, you're good. If it is there, then call remove on it. Because you see how, like, you're doing what the user wants in that case with the nitty-gritty details that are part of your private methods that the user does not get to notice. Okay? That's just for you. These are all private methods in the private section. All right? So that's a nice separation of concerns there. So release will call remove. We good so far? Like, are there questions? This is a very involved lab. You have to read through all this code, go look at your book, right? Go back to our slides. There's a reason there are a few weeks for this lab. Do not do it at the very end. You will not get it done in time. All right, and then there's one last thing that I've implemented for you. It's a function called it's a method called toGraph that turns your tree into a format that you could visualize it with, and I will show that to you in a second. Okay, so it's a very long function. I worked very hard on it to get it working, and I tried to not dereference null just in case your tree is wonky and you have problems. I'm going to do the best. All right, so I think that's all that I wanted to say for all that. You got a bunch of tests. They're in BST tests, so like that's the makefile that will compile it for you. It's going to include your library and run a bunch of things. So here are all my tests. Boop. So I've got a bunch of Pokemon that I'm going to like insert. So we've got a bunch of tests here. So like at the beginning of time, there should be nothing in the tree, right? Constructor should have made it empty. And then I'm going to add all the Pokemon in this list that are kind of out of order, and they should be ordered now because it was a binary search tree when I go and get them back, okay? So that's that. The searching process, just like make sure the things that are in there are in there. They're all in there. Search for something that's not there, should give back null because it's not there, right? And then removal should correctly get rid of things. Like if I get rid of Pokemon number 6 should not be there anymore. If I get rid of Pikachu should not appear in the in-order traversal's output. Stuff like that, all the way down to the empty tree once you've got rid of everything, okay? So it has to be precise to get all the tests to pass. You will probably run into a million seg faults, all right? GDB is your friend. I'm going to remind you how to use that. I'm going to show you something cool as well. So, yeah, are there any questions about what your job is? All you're doing, you don't have to write any tests. You're implementing the binary search tree BST class in bst.cpp. That is all you're turning in. Does that make sense? Make enough sense? So you have to wrap your mind around what's going on. It's just like keys are ints, values are this object that I've called Pokemon. You don't have to really worry about that too much. And then the rest of the trees, you got your left, right, and parent pointers. Okay, so those are all there. And let me show you what's going to happen. So eventually, you will have a seg fault, or you'll have a test that doesn't pass, and you have no clue why. Okay, so let's pretend that has happened. Let me really quickly copy this all somewhere. Let me go very quickly to AutoGreeters 41. Lab 8 solution. Let me copy all that to like my home folder /lab08 solution. Boop. So here's my solution, make BST test. Boop. So there it is. Like, eventually it will pass. Like, you want all the tests to pass, but let's say they didn't. Like, you want to see passed everywhere. But let's say they didn't, all right? What you will do is you will run your code, like, if as well as if there's a seg fault, you should be going and using GDB. Every time you see a seg fault, go and print out what's going on, all right? But if you don't get a seg fault and the tree is just wonky in some way, even if you do get a seg fault, you might be able to use what I'm about to show you. I've made a very nice little helper method called .toGraphViz, all right? So there's a website called webgraphviz.com. What GraphViz is it's a textual format that lets you draw stuff. And so I'm able to output your tree in that textual format that will let this website draw it for you. It will draw a picture of the BST that you made. All right, and so then you can see like, oh, the left and rights are not what they should be or something. The tree is not as it should be. So let's say, because it's probably going to be removed, that's going to mess with you. You go to the tests, like, all right, I failed the first removal test. That was test release or something. Like, all right, the first removal test did not pass. And so what you want to do is you kind of want to look at the tree right where it didn't pass. Like maybe you got a seg fault even, like this is what the tree should look like. Maybe this call fails for some reason. Like the test either doesn't even get to the test because it's seg faults, or it does and like the tree is wrong. So what you can do is you can stop the program right there after that's finished, or if it's seg fault. So let me just be like cout star null pointer or something to force it to end right there. All right. Will this compile? I'm not actually sure. Let me do something like that. No, darn. Let's do like, I don't know, int star x equals null pointer. This is just me getting a seg fault easily. But say that your release method did that. All right. You could also just add this in to stop the code right there in GDB if it did work, but it still did the wrong thing. Like that's a way to do it. Like I am now forcing the program to stop on that line, right? After this release is finished. So let's say that something was wrong right there. So compile it. You run it. It's like, oh no, there's something wrong with the test. It didn't work. I got a seg fault, or I didn't, and I added it in to stop the program right there. Let's run this in GDB. So you say GDB, pretend to run the program. You're like, okay, run it. It stopped on the seg fault, of course. If it was a real seg fault, you could look at the stack with BT and be like, all right, what was going on? Where was I? But now I'm in that file. We've got here. Let me just vim it. Window lab 08 solution bst tests.cpp. It's going to complain maybe. Well, here I am. And it's building up a BST called B. All right, it's building up a BST called B. And I have made a bunch of methods, one of which is called, in your tree, it's called toGraphViz. Okay, so there's that. And you can ask for it to be run. All right, so gosh, how can I show this to you? So I need to now look at, I need this and then the original blank bst.h or bst.cpp. So here, if you have a tree called B, you can ask GDB to run the toGraphViz method on it and print out the string that it has in it. Right? You can say call puts b.toGraphViz and it will print it out for you. And then you can load it into this webgraphviz website. And so let me show you all that. I've made some slides about all this. The first thing I want to show you is a different way to do everything. So here, let's say if you didn't get a seg fault, there's a better way than to just add a seg fault right there yourself. Okay, it's called a breakpoint. So let me have you do it the right way. So let's say, okay, there's something wrong with line 87 of bsttest.cpp. Yes, something wrong. It does not do the right thing. So I would like to stop the program after that line is completed. Does that make sense? Like I want that program, I'd like to look at GDB. I want to look at the contents of the tree after line 87 is done. All right. So if your program runs and it just fails and you're not sure why, GDB will just let it run unless you use a thing called a breakpoint or you add in a segfault like I just did. That's another way. All right. So a breakpoint is probably the better way to do it. It's a line number where you tell the GDB to stop your program. So before you run your program, you can load it into GDB. You load it into GDB. You say GDB, pretend to run the thing, tests. And before you say R for run, you can set it up to stop after this line. You can set a breakpoint. You can say break and then space, the name of the file, colon, the line number you want to stop on, colon 99 or whatever. So for us, we can say break or just bst tests.cpp colon. I want it to stop after this is completed because I want to see what the tree looks like. So stop on line 88, please. Does that make sense? So I'm telling GDB to stop on that line by setting a breakpoint. Break on bst tests.cpp line 88. Hit enter. And then the program is not yet running, but now I can tell it to run. And it's right there. It's like, all right, I just ran this line. I'm about to run this line. What do you want? So stop the code right there, even though there was no segfault. So I can inspect the code, what's going on in the tree right now. Does that make sense? How that's very powerful and important, and how we're going to want that. So now you can start printing stuff, or you could ask it to continue and like do things. So let me show that. Let me just do this for you right now. Like if you stopped it there, you can say print, like you can print the B. What is your B type, but something that has a root? You can go look at the root, like print B, B's root, or B dot root. Like you can access any private thing in GDB. GDB doesn't care. Like this is just for you, right? So like there's the root. Let's dereference it. It looks like the key is 5. This is the data value. It's this Pokemon. It's got a left and it's got a right. You can move around the tree yourself by printing. That's kind of nice, yeah? Does that make enough sense? Like that's important. You want to be able to do that. What else? So you can go look at the tree like that. Or if like the release was doing something weird, you can walk through the release by setting a breakpoint on line 87 before it goes in. So here, let's do that. I'll restart it. I'll say break bst tests.cpp line 87 right before it runs that line now. So hit run. Now it's right about to run line 87. And here's the next cool thing that you can do. If you had your program stop with a breakpoint and it's not done yet, so please keep coming back to these slides. These are very important things that you can do in GDB. So you set a breakpoint. It stopped. The program has not crashed, so it can continue. You kind of want to watch it work and see how things change. You can say any of these. So next runs the line of code that it's about to be run to completion. So it will jump over this call and complete that entire call to b.release Pokemon. If you say next, it will move on to this line in the same function/method you are in. Like this, of course, is going to call a bunch of things, but it's going to jump over it. It's going to complete it. Next, get on to the next line of wherever I am right now. All right. That's what next does. Step is more fine-grained. You can say step to run one step of execution, maybe going inside of things. If we're about to call something, like go to that code. So I don't want to show you too much, but like you can say step. It's like, ooh, search. That was the first thing that we did. And then you can step into the search. This is about to be called. Like that's the next line. So now we step. Now we just called search. And you can watch all your code unfold at the smallest fine-grained detail as you'd like. So some combination of step and next, like I know that search worked. I could have just said next there or something like that. But if I don't trust search, okay, let's step through search. Step. Well, it's not null step. So I'm maybe giving away a couple lines of search, but that's okay. You can see like a print n. You can watch it work. Does that make sense? Like, that's very powerful. Next moves over the line in the current place. Step goes in if it needs to. So you have to be careful before you call something in a library because then it gets into disgusting library code. You didn't want to step into that probably. So you can do that. And then C is for continue. It continues until the next breakpoint or until the program crashes or the program is over. So C just like continue until I need to stop again, either through a breakpoint or an error. So C for me would just complete the entire program at this point. But yeah, we can set another breakpoint. We can look at the tree again. So let's say after 87, there was something wrong. So let's set a breakpoint on 88. So break BST, because we can restart this program. Break on line 88. So now there's actually 2 breakpoints. There's one on 87 and 88. So if I rerun it, it's like it stopped on 87. Like, okay, just let it run. Next, get to 88. It would have stopped there anyway. I could have said continue actually. So here I am, and all right, I want to print the tree. So here's what my toGraphviz does. So you could say, you can actually ask your B to do whatever. Like, hey, B dot do the things that we can do to B. Print B dot, and it knows. Print B dot root. You can ask it to search for something. Print, I don't know, print B dot ordered list of Pokemon. Like, you can call it. It's like it'll give you back the answer. It'll run the code for you if you want it to. Like it's like it's adding that to your program. That's pretty neat. So you can ask it to call any method, one of which is my toGraphviz method. All right. So you could have said print b.toGraphviz. That's not good enough. Sorry for all these lines. Why are you not happy? Why is it lowercase? B dot. Oh, oops. Now it's very unhappy. Can I not do the original thing anymore? Oh, goodness. Enter it. Where am I right now? Okay, yeah, because we tried to call it, it's gonna mess up. It's gonna do weird things if you try to do it that way. Let me just restart the program. Restart, yes, continue. So now I'm at line 88 again. So I could say, you could say print b.toGraphviz. That really will work. It will do the right thing. It will compute the string that I'm trying to compute for you and give it back to you, but it's gonna say dot, dot, dot. It's not gonna give you the full thing, unfortunately. It's just gonna give you a piece of it. So instead, what you do is this. You tell this line to exist. All right, it's weird. You say call this function, call puts, puts. It puts a string onto the output screen of the result of b.toGraphviz. It will take the string and print the whole darn thing out to the screen without cutting any of it off, because GDB was cutting things off. All right. So that's all you do. So if you have a tree called B, which is what the tests are calling them, you say this and it will run the toGraphviz method on your tree and print out all of this. This is your tree as a thing, all right, as something we care about. And unfortunately, I want to copy and paste this. I need to make it real small. But what you want to do is you want to take this output between the equal signs, between that one and this one down here. You want to take all of those and you want to copy and paste. So I need to, oh goodness, copy and paste all of those onto webgraphviz.com, this website. Okay, watch me. All that, copy, paste, generate graph. It will draw the tree. So if your tree is wonky, it looks wrong, you can compare, like, oh, like this was maybe something, like maybe this was over here accidentally. Oh, something that was smaller is now on the left, or my entire right subtree is gone, but all this is over here. Like something is wrong. You can look at this. All right. This will tell you your tree. It'll also tell you who the parent was. The parent was 5. Parent is 5. Parent's the key value 25. Because sometimes your parents are off, and that's going to mess with a few operations, right? So this is saying left and right are null. These dots are just null. Correctly, nothing is there. Okay. So if there is something wrong with your tree, stop with a breakpoint. Tell GDB to print what the tree looks like in the GraphViz format so you can generate it and look at it as a picture form. Do you see how that's going to save your life? It's going to be very helpful. So I worked hard on that for you. Please use it. Okay? So you just got to say it like this. It's a little weird of an incantation, but that's how it works. And I think that's what I wanted to say. So if we are happy, I believe that's all that I can do. Use that, take advantage of it, stop your program where things go wonky in GDB with a breakpoint, and then tell it to print out your tree like that. Or you could also step through it and watch it either work or not work, right? You can step through it to see how you got somewhere, and you can start printing out the tree, like, all right, what's the roots left now? Let the line run with step or next. Okay, what's the roots left now? You can see what's there. You can see how it changes, and you can compare against your mental model of how things should have worked, right? Because that's all debugging is at the end of the day. So GDB is very powerful. This is the next step. You know how to deal with seg faults. This is the extra stuff, right? These are extra things that let you watch the program unfold, and that lets you debug in an even more powerful way. Okay? So I think that's all that I wanted to say about that. Are there any questions about our Lab 8 and what your job is? It was very involved, but I hope you see it. So the only thing you're turning in is the .cpp file. And so, yeah, if we're good, I think that's all that I've got for us. Remember to start early. Don't let this meme be you. And yeah, I will stop the recording now and give you all the stuff.